Hi. Last lecture on this is the Doppler effect. And I'll actually post, I always post supplemental videos, but I'll post some specifically about the Doppler effect. And one of the things I usually do for this in the classroom, and I'll probably do this if we come back hopefully on Monday for face-to-face, is I actually took the alarm out of a fire alarm and uh, and it's already been tripped. So as soon as you put a battery in, it starts screeching. But I have it on a string, and if you spin that on a string, the fire alarm gets closer and farther and closer and farther, and it actually allows you to hear like what the Doppler effect is like. Because what you'll hear, even though if I hold it still, you hear ee, but if it moves, it goes ee. It changes. Sorry if that was annoying through the thing. And that's the Doppler effect. The Doppler effect is the change in frequency or pitch, which is how we subjectively hear frequency, of a sound detected by an observer because the sound source, the observer, or both are moving. And you just have to be moving different to one another. You have different velocities. All right. And the way this works, if you have a moving source versus if you have a moving observer. All right. And I'm just going to show you the different equations. So this is the frequency that the observer hears is equal to the frequency of the source. Now, if neither one of you is moving, this is true. You hear the source as it was intended. If the source is moving, we get this equation. And v is the velocity of sound in that medium. Okay? I think I have one where I kind of say that. Yeah, so there's the equation. This is when the source is moving towards you. Notice how it's a negative. And this is, so source moving towards you. So if you're the observer and the source is moving towards you, it's subtracted here. And so we can do a plus and minus here. It's minus if the source is moving towards you. If it's positive if the source is moving away. So if it's plus, then this denominator is going to get bigger, right? And that's going to make the frequency appear smaller. So if it's moving away from you, that's actually going to make the wavelength bigger, which makes the frequency smaller. It's similar to a redshift. As light moves away from you, it shifts towards the red. As sound moves away from you, the wavelength gets longer and the frequency gets smaller. The source frequency stays the same. It's the frequency that you hear changes because the wave is actually being stretched out as the source is moving. This is how movement affects waves. And like I said, this is going to be related to when we get to electromagnetic radiation to the red and blue shift. If an object is moving away from you, it shifts towards the red. If it's moving towards you, it shifts towards the blue. Same thing is happening. If it's moving towards you, this number gets, we get a smaller denominator, which makes this number bigger than 1. 1 divided by a number smaller than 1 is a number bigger than 1. So the frequency you hear gets bigger because the wavelength is getting smaller. So let's look at an example. A high-speed train is traveling at a speed of 44.7 meters per second when the engineer sounds the 415 hertz warning horn. So that's frequency of the source, 415 hertz. The speed of sound, Vs, V is the normal velocity of sound. Okay, which is usually 343 meters per second if we're 1 atmosphere and 20 degrees Celsius. So basically standard temperature and pressure are for these types of questions. All right, the speed of sound is 343 meters per second. That tells us we're in 20 degrees Celsius. What are the frequency and wavelength of the sound as perceived by a person standing when the train is approaching? So when the train is approaching, we use minus, and when the train is moving away, we use plus. So the source is 415 hertz. If it's moving towards us, If it's moving towards you, you use minus. So that's the top one there. And the velocity of the source is 44.7 meters per second, and the velocity of sound is 343. I put that into the equation. The frequency heard as it's approaching is 477 hertz, and as it's going away, it's 367 hertz. That's why when a vehicle passes you, you hear, and you hear a difference when it's right in front of you because of the differences in angles, but when it's coming, it's pretty standard. But it's pretty constant when it's far away in each direction. Okay? So you hear a different sound than the source based upon movement. Now, it doesn't have to be just the source that's moving. The observer can also be moving. And when it's the observer moving, you notice how it's, and I'm just going to do one equation here now. Because what I'm going to show you is that if it is if the observer is moving, you actually have this 1 plus or minus V naught. It's V naught over V because you're the observer is in the numerator. And the reason for that is because it's really just F of naught divided by 1 plus or minus V naught over V is equal to, let me redo this. The frequency of the observer divided by 1 plus or minus the velocity of the observer divided by the velocity of sound. I keep messing that parenthesis up. Frequency of the observer divided by 1 plus or minus the velocity of the observer divided by the velocity of sound equals the frequency of the source, basically divided by 1 plus or minus the velocity of the source divided by the velocity of sound. I just can't get those parentheses right. Okay? And when I put those together, we get this equation. The frequency heard by the observer equals the frequency heard by the source times 1 plus or minus the velocity of the observer divided by the velocity of sound. So if the observer is not moving, this is 0, so it turns to just 1. And if the source is not moving, this becomes 0. 1 plus or minus 0, 1. If the source is not moving, this goes away. This equation here gives you every possibility. And like before, you'll see that it's minus if the source is moving towards you. So minus source moving towards you. S moving towards O. Positive is when S is moving away from O. And something like this is what you're going to want on your like 3x5 for the test. These are things that you want to know. Okay, and then but for the observer, it is positive when the observer is moving towards O, moving toward S, and it is negative when O is moving away from S. So the plus minus changes, and the reason for that is simply because it's the perspective difference, right? It's the observer moving instead of the source, so the directionality changes, right? But this gives you every possibility. Now, if both of you are moving, then you have to have both of these functions. If the source is moving towards you, then it would be 1 minus velocity of the source divided by velocity. And if you were simultaneously moving towards the source, then you would have 1 plus V naught over V. So it'd be 1 minus Vs over V here because the source is moving towards you, and 1 1 plus V naught over V here because you were moving towards the source. Both of them matter. So you end up with this equation right here as the general case. So this slide right here will answer every question I could give you or that I would give you on the Doppler effect. In college, you might get a little bit more complex because you may need to remember also that velocity is frequency times wavelength. So in college, they might throw a caveat at you where instead of giving you frequencies, they give you wavelengths, and you have to convert those into frequencies first. I'm not going to mess with that kind of stuff. Or they might change the temperature of the air so that you can't use 343 for the velocity, but I'm going to give you that velocity. All right, so that is the general equation for a Doppler effect. And we use this for many things. We use this in ultrasounds, is basically using the Doppler effect to trace images. We use ultrasonic waves to vibrate things, to shatter tumors. I mean, we make use of this in many ways. We can actually use Doppler effects to figure out where blood is and where blood cells are and all that kind of stuff, to do carotid ultrasounds and stuff like that. So we use this for a lot of things. So here are 5 more questions. If you can do these questions, you understand everything. If you want to try them out, you don't have to. But that's it for the Doppler effect. And that's it for this chapter. I may or may not post a review video that goes over, well, I probably will post a review video that goes over the review guide, at least in terms of the questions on there. However, as this is a new I told you guys everybody did really well. They got all of their review guides in. Not a single person that I can remember didn't get the review guide in. It might have been late, but everybody eventually did the review guides. That there's no homework for this semester unless people's grades start to drop. There's no homework. But I'm just going to give you suggestions for things that you can do. There are still self-test questions on the review guide, and you definitely want to make sure that you know how to do those self-test questions because questions like them will be on the test. So I may post another video where I just go over those self-test questions, but it will not be until after or on the day of review, so usually the day before the test. So you definitely want to try them before then, because if people aren't doing the review guides, then I'm going to have to start assigning it again. So that's all for now. I hope you, if you're watching this on Friday, I hope you have a good weekend.